Welcome to today's practical. Today, we return to the lab to explore how changing reactant concentrations can alter the speed of chemical reactions. Before we get started, remember to put on your lab coat, safety goggles, and gloves. Safety is crucial in the lab. Let's quickly revisit some of our previous lessons on rate of reaction. We've explored what chemical reactions are and how to calculate their rates. We've also introduced collision theory as a model of the mechanics underlying these observations. Now, we arrive at today's engaging practical, which will give us hands-on experience in testing how different reactant concentrations impact reaction rates and how to measure this. We're almost ready to dive into the details of our practical, but first, let's explore why this experiment is both exciting and valuable. Firstly, understanding how reactant concentration affects reaction rates is a critical concept in numerous fields. From pharmaceuticals, where reaction rates determine the speed of drug production, to environmental science, where reaction rates can influence pollutant breakdown, mastering this concept is essential. By conducting this experiment, you'll see firsthand how changing concentrations can expedite or slow down reactions, equipping you with insights that are directly applicable in these and many other industries. Secondly, you'll employ two distinct methods to measure reaction rates: the volume of gas produced and the observation of color or turbidity changes. This dual approach offers a comprehensive perspective on reaction rates and enhances your analytical skills. Understanding different methods of measurement is key to developing versatile problem-solving abilities, allowing you to select the most suitable approach for any given situation. On to the practical. Let's start by gathering our materials. Sam, what do we need?
So for this practical, we need a mass balance, a measuring cylinder, a stopwatch, a gas syringe, a sheet of paper, a pen, a thermometer, a conical flask, and a lab book.
Let's get started. Make sure your lab area is tidy and all your materials are within easy reach. For the first experiment, we will be investigating how changing temperature affects the reaction rate. We'll be looking at the reaction between sodium thiosulfate solution and dilute hydrochloric acid. Here is the chemical equation for this reaction. As you can see from this, one of the products of our products is sulphur, which forms as a yellow-white precipitate. We'll exploit this fact as a way to measure the reaction progress. Here's how we do it. To get started, take a measuring cylinder and carefully measure out 50 centimeters cubed of dilute sodium thiosulfate solution. Once you have that ready, pour it into a conical flask. Next, place this flask on a piece of paper with a black cross drawn on it. This will serve as a visual reference for our experiment. Now, grab another measuring cylinder and measure out 10 centimeters cubed of dilute hydrochloric acid. Pour this acid into the conical flask with the sodium thiosulfate. As soon as you add the acid, swirl the flask gently to mix the contents thoroughly. At this moment, start your stopwatch to track the time. While the reaction is taking place, measure and record the temperature of the mixture using a thermometer. Then, look down through the mixture and keep an eye on the cross beneath it. When the cross is no longer visible due to the reaction, stop your stopwatch and record the time. Measure the temperature of the reaction mixture once more and make a note of it. You will repeat steps 1 through 6, this time using sodium thiosulfate solutions at different starting temperatures. This will allow you to observe how temperature influences the rate of the reaction. After you have done this, you should have a table of data that looks something like this. We can add a third column for reaction rate, which we calculate with the equation, 1000 divided by time for each temperature. This value is proportional to the rate of reaction. Finally, we can better understand this data by visualizing it with a graph. In this case, let's use a line graph with a curve of best fit. We'll put the reaction rate on the y-axis, as it is our dependent variable, and the temperature on the x, as it is the independent variable. Looking at this graph, we can see that the rate of reaction increases as the temperature increases. Additionally, notice that the rate increases by a greater amount at higher temperatures. This fits the predictions of collision theory, as reactant particles both have more collisions, and these collisions have a greater energy. Before we move on, there are a couple of things we need to consider with this experiment. Since we're heating the sodium thiosulfate solution, it could spill and cause burns to the skin. Accordingly, we should handle it with care and not heat it above 60 degrees Celsius. Additionally, another product in the reaction is sulfur dioxide. This can cause irritation to the eyes and lung, especially for people with conditions like asthma. Accordingly, we should ensure the room is well ventilated and avoid breathing directly over the top of the flask. Finally, we measured the reaction progress by waiting until the black cross was no longer visible. However, two people might have different opinions on whether the cross is still visible at a given moment. Accordingly, it's important to have just one person measuring this across experiment trials. Even then though, basing a reaction's progress on something like whether a cross is visible is very subjective and allows for a lot of human error. But with this in mind, let's consider our second experiment. With this experiment, we'll be investigating how concentration affects rate of reaction by looking at the following reaction between calcium carbonate and hydrochloric acid. As you can see, one of the key products of this reaction is carbon dioxide. As such, we can measure the volume of this gas to determine the reaction rate. Here's how we do it. To begin, take a measuring cylinder and carefully measure out 50 cubic centimeters of dilute hydrochloric acid. Pour this acid into a conical flask, which will be the container for our reaction. Next, set up your gas syringe using a stand, boss, and clamp for stability. This will ensure accurate measurements as the gas is produced. Now, it's time to introduce the reactant. Measure out 0.4 grams of calcium carbonate and add it to the flask containing the hydrochloric acid. As soon as you have added the reactant, secure the gas syringe with a bung to ensure that any gas produced is measured by the syringe rather than escape into the air. Once this has been completed, start your stopwatch. This is crucial, as it marks the beginning of our observation period. During the reaction, we need to keep track of how much gas is being produced. Record the time it takes to produce every 10 centimeters cubed of gas. This will give us valuable data on the rate of reaction. Now, to deepen your understanding of the reaction dynamics, you will repeat steps 1 through 5 using different concentrations of hydrochloric acid. This will allow you to observe how concentration impacts the rate of gas production. We will have recorded our results with a table like the one displayed. This allows us to note the time that each volume of gas is reached. From this, we can calculate the reaction rate using the equation 1000 divided by time taken. For each concentration of hydrochloric acid, we will also plot a graph to show the volume of gas on the vertical axis, the time on the horizontal axis, and a curve of best fit. For each concentration of acid, we can also calculate the mean rate of reaction until the reaction stops. This is given by the equation total mass of gas divided by reaction time. We can determine when the reaction stops by looking at our graph. The point at which the curve flattens is when the reaction has completed. With these calculations and graphs ready, we can see that increasing the concentration increases the rate of reaction. Specifically, the curves of our graphs are steeper when the concentration is greater, and the value for our reaction rates are greater. Again, this finding matches the predictions of collision theory. When the concentration of a reactant is higher, there is a greater frequency of collisions, leading to a higher reaction rate. In today's lesson, we embarked on a practical investigation to explore how to measure the rate of a chemical reaction, delving into two distinct methods. Firstly, we turned our focus to changes in turbidity during the reaction between sodium thiosulfate and hydrochloric acid, using the emergence of sulphur to measure reaction speeds. Secondly, we examined the reaction between calcium carbonate and hydrochloric acid, measuring the volume of carbon dioxide gas produced to gauge the reaction rate. As we continue to conduct practicals in chemistry, remember the importance of precise measurements, consistent methodologies, and safety protocols. Embracing these principles will refine your skills and deepen your understanding in future experiments.